Hello and welcome back. In this video, we're going to talk about modeling of chemical processes with an emphasis on dynamic modeling. And the content of these slides is going to come from chapter 3 of Chemical and Bioprocess Control by James Riggs. The slides here are adapted from some of the content that the authors provided. All right, so just a quick overview. I'm going to be sharing some information here, but I'm not going to go in detail on some of the texts that are a little bit wordy. You're welcome to pause and just kind of read through some of the ideas and then move forward. So, in general, as a chemical engineer, when we look at chemical processes, we generally tend to study processes at steady state, which means is that there's no accumulation within the system. So what comes in goes out. Um, these models are important for things like sizing equipment, determining how much a process responds in response to a change in an input, and repeated solutions of these can provide a variety of information about processes. Dynamic models, on the other hand, are useful for determining how fast things respond, how much things respond, and which process inputs are most important, and also which terms such as system volumes, flow rates, temperatures, etc., have the largest effect on the overall process. So the use of dynamic models is pretty common, especially when we look at batch processes. So when we study our reaction kinetics, we'll look at reactors where you just fill them up initially, heat them up, and then let them go. And in these processes, what you'll see is that the concentrations will change as a function of time as the reactant is consumed and as the product is made, depending on what the temperature aspects of the systems, whether it's adiabatic, isothermal, isobaric, etc. Some of the other terms in the system, such as temperatures and pressures, and potentially even reactor volumes, can change as a function of time as well. And so these are useful for such systems. Also importantly, for process startup and shutdown, the use of dynamic models is extremely important. For process dynamics and controls, or for controlling a process, it's important to understand the dynamics, because we really have to tell the controller how much and how fast to respond to disturbances that are going to affect the process. So we need to know how flow rates and temperatures affect the process, such that in order to be able to control the processes, to keep them at target set points. So there's two different types of models that we can treat. Generally, we're going to focus on lump parameter models. And what a lump parameter model is, it's a model that assumes that there's no real spatial variation within the process. So for example, a perfectly mixed reactor, inside the reactor contents, the temperature, concentrations, compositions are staying the same. In these cases, the only thing that can really change or these variables can change as a function of time, but with respect to spatial position, there's no variation within the process. So these are convenient because we can treat processes as just a single thing and focus on inputs to the process and outputs from the process without worrying about exactly what's going on inside the system. The lump parameter models, these can apply macroscopic balances, and we'll use conservations equations, particularly mass and energy. From the mass equation, we can look at mole equations as well. And in general, these forms will either be algebraic, for example, if it's a steady state system, or an ordinary differential equation if we're considering the dynamics. So here's an example of a lump parameter process. This is an example of a thermal mixer where there are two streams entering the process. So here we have stream 1 that's at a given temperature, and stream 2 at another temperature, and then an outlet stream from the process. So in the lump parameter model, what we assume is it's well mixed, and the temperature inside here is constant. We also can assume things like, maybe constant volume, perhaps maybe assuming things like constant density, Again, density is a function of temperature. And when we think about these types of systems, one of the things, the reason for doing this process is because we care about having a known temperature coming out. So this outlet heat stream needs to be set to a known temperature so that it can be fed to a reactor or a separator or something like that. So if we were going to apply process controls to the system, we're measuring the temperature here. So this TT is a temperature transmitter. So it's a sensor combined with a transmitter. This will tell us the temperature. Our manipulated variable, okay, so this would be our control variable, or sometimes it's called our process variable. And then our manipulated variable is going to be the flow rate of stream 1 into the process. So what we can do is we can change this valve position here, which is going to affect the temperature in the system, which is going to affect the outlet temperature of the system. So in terms of process controls, is we would need to have some sort of, we could have a controller, we could have a specified value of the temperature. So this temperature sensor goes to the controller, and this controller might go to the control valve. So changes in the temperature are going to be received by the controller, and the controller is going to tell the valve to open or close. Without a controller, in a sort of a manual control mode, as the user, an operator may monitor the temperature and manually make adjustments to the specified flow rate right here. So this right here, F1 specified, could be a user specified value, or it could be a value specified by the controller. So in one case, you might imagine watching this process. If the temperature changes, you'll adjust the valve position manually to keep it where you want it to be. But really what we want to do is learn how to be able to automate these types of things. Okay, so then now a distributed parameter model, and we're not really in our class, we won't really discuss these or use these for process control because they're not as useful. But a distributed parameter model is one that considers spatial variations within the process. So this is going to include include variations in mass. So if there's mass transfer effects or variations in temperature, from maybe the innermost part of the heat exchanger to an outermost part of the heat exchanger, or the temperature in a heat exchanger is going to vary as the fluid flows through the heat exchanger. There's various systems where if you look inside the process, we know that there will be variations in mass and temperature inside the system, and models that treat that variation inside the system are what are called distributed parameter models. And oftentimes, if we want to solve for the dynamic behavior of just distributed parameter models, we have to use partial differential equations if multiple dimensions and time are considered. So let's just look at a heat exchanger, for example. So in a heat exchanger, we have a flow rate, a process flow rate coming in, and it's going to enter the process at a specified value. Let's call that T naught. And this fluid is going to go through this heat exchanger, and it's going to exit at a temperature that we care about. So in this case right here, we're calling this T outlet. That's what we care about, and so we measure that. So as this fluid flows through this process, if it's a shell and tube heat exchanger, so on the outside of the tubes is going to be steam. So steam is fed into the system. We have a valve that we can control the steam flow rate or the steam pressure. Now we know that let's say the pressure of the steam is related to the temperature of the steam, and the temperature of the steam is what's accounting for the heat transfer in the process. And as the steam, particularly if it's saturated steam, as the steam transfers heat to the process fluid, it's going to exit as a steam condensate. So in this process right here, we have a delta T, which is a difference in the temperature of the steam and the temperature of the process. And I'm going to write this as I, because what we know is that as the process fluid travels through this tube, the temperature is going to increase. So for example, if the feed is entering at 25 degrees C and exiting at, let's just say 90 degrees C, there's going to be a temperature profile of this of the process fluid as it travels through the steam. If we treat this as a distributed parameter model, we're going to have to account for that spatial variation through the tube. If we treat this as a well, okay, let's look at what the question is saying. If we're treating this as a steady state model, at a steady state model, there's no variation in time. We just have constant inlet, constant outlet temperature, and then we can calculate what the temperature profile is in the system, assuming that there's no variation. A lumped unsteady state model, we could take this whole system right here, and we could treat this really as like a black box and just say that, we could write an overall balance on the system. So we have a change in temperature of the process fluid, and we can relate that to the amount of steam that's condensing in the process. And that's useful for knowing how would we need to adjust the steam flow rate or the feed flow rate to keep the process at a given temperature. And then for a distributed unsteady state model, right, we would have to do a partial differential equation to account for how the system, how the temperature is changing throughout the process, as a function of how the temp. So changes in temperatures are going to cause changes in heat transfer at a given point, which is going to affect the overall process. And again, for what we're doing in terms of practical process control, there's really no need to go into that type of detail. So we're going to generally focus on the lump parameter models. And we can also think about these distributed and lump parameter models just based on different types of reactors. So for example, if we look at continuous stirred tank reactors, CSTRs have the assumption of constant volume and well mixed. And what well mixed means is that there's no variation in temperature and concentration of a given species inside the reactor. So we would assume that the concentration of species A, which is the reactant, is constant throughout the system. Therefore, the temperature is constant. Going into the next system, again, we would have this constant, let's call this T1 up here, Ca2 at T2. So again, in this system right here, we have a constant concentration at a different concentration, but also a constant temperature in this system. So we would treat these as essential no spatial variation inside these systems, and we can just look at inlets and outlets of the process. For a plug flow type reactor, in a plug flow reactor, we generally have concentration entering the system. And then as we travel down the reactor, the concentration of the species A is going to decrease as we go from the entrance to the exit condition, because we could treat each individual element of this reactor as no spatial variation. So we would have a constant volume, so a given volume I where the concentration will decrease. So throughout this reactor, our concentration is going to decrease depending on what the reaction kinetics are for that system. So in this case right here, there can be both spatial variation and time variation in this type of process. But again, we could also treat the PFR as a lump parameter model and just look at inlet and outlets for that overall process. Okay, and just sort of a side note here, one of a method or a sort of a phrase that we can remember to help, how to solve chemical engineering type problems is through the use of what's called the SOMS method. And one of the things, especially in process dynamics and control, it's important to draw a sketch or picture, represent the process that you're studying in a picture mode. So for example, if you're looking at how to control the level in the tank based on an outlet flow rate, let's just go ahead and draw a tank. We have inlet flow rate, we have outlet flow rate. If we're controlling it based on the outlet flow rate, we would have a valve. So we would know, for example, our control variable is the level, and then our manipulated variable is F out. Right, so I think you're just representing the process as a picture. Then define the system. So again, if we're thinking about a level, our system right here is going to be the contents of the tank and this is the level. So we have the thing, we can look at what enters the system, which is the flow in, and what exits the system, which is the flow out. Identify relationships that are always true. So we might have things, or we might have um, things like, volume equals the cross-sectional area of the tank times the level, for example. I mean, that would be an example of the physical. Wait, so that's the cross-sectional area times the level is the actual volume of the system. What else do we need? So other types of models is we know that the mass is also going to be equal to the density times the volume of the system, so the mass of the stuff that's inside the system. We also have other models like that can relate flow rates. So if we have to relate mass flow rate to volume flow rate, etc., and then solve the resulting equation. So again, we have and then also, yeah, so I should also say here models. And I didn't talk about the most important one. One of the models for this, we would have to include the conservation of mass. So for example, we know that the rate of change of mass accumulated in the system is m in minus m out. And then we would go ahead and convert that model into measurables using known relationships and then end up solving. So we have picture system, identify always true models, and then solve. All right, so let's start with our mass balance equation. So our first conservation equation is mass balance. And what we can do is we can write the mass based on total mass, or we can write the mass of an element, for example, carbon, oxygen, hydrogen, or we can write mass balance on individual species so long as there's no reaction occurring. Another way that we can convert from the mass balance to the mole balance, or we can balance moles by just writing the mass balance and dividing through or multiplying through by molecular weight. So in general, we have the rate of accumulation of mass in a system, dm dt, equals, it's going to be the sum of mi in. So I'm writing m sub I right here and m dot to represent a mass flow rate, minus the sum of mi out, because we can have multiple streams entering, we can have multiple species entering. There's various ways that we can write these types of systems. So sometimes this can be represented as f could be written as a flow rate. And again, it's just important to know what are the terms, or what are the terms that the author of the sources that you're looking at is using in order to represent the different types of flow rates. So mass balance, that's kind of a little bit straightforward. So mole balance equation, and again, I'm not a fan of the term mole balance because moles don't necessarily equate to each other. So I would prefer a mole relationship equation. And again, just precision in language, and a mole relationship equation accounts for chemical reaction. So if we just go from if we look at a given species, for no reaction, we have the rate of change of the moles in a given species of A equals, I can write this FA naught. And again, this is going to be moles per time. And here FA naught is going to be a molar flow rate, equals minus FA. This is going to be the number of moles that exit the system. And then we can have a rate of generation of moles through reaction, and that's generally going to be expressed as the integral of RA dV over the volume, where R is the specific reaction rate. And then again, there can be, it's not necessary to distinguish the difference between generation and consumption. Some people will just use one term here, and they treat consumption as a negative generation. So in spirit of this equation, we can say plus RA generation minus the integral of RA consumption over the volume dV. And again, this would just be a negative term. So The way I will generally derive the equations is I will ignore these terms, and I will treat reactions that involve generation of species A's as positive terms, and I'll treat reactions that involve a consumption of the species as a negative term. And you can have as many generation terms as you have that species participating in chemical reactions. So generally, because we're using lumped parameter models, this term right here, we say there's no variation in things like rates or concentrations, temperatures over the volume. So this term just becomes RAV. And again, for reaction kinetics, we'll tell you what the reaction rate is for this class, but just as a reminder from a reaction kinetics or physical chemistry class, you might have seen things like for first order reaction of species A, RA equals KCA. Second order reaction is just KCA squared. And again, these are additional things. And for what we're doing here, any problem that you'll look at is we'll tell you what the reaction rates are for a given system. Now we can also make it more fun. So we can add temperature effects too, because this specific rate constant K can be expressed as a function of temperature through the Arrhenius relationship where K equals K naught, or we could say this could be A naught, exp to the negative EA, which is the activation energy over RT. So we can write this as a function of temperature if we expect that the reaction system the temperature will fluctuate enough that it will actually affect the specific reaction rate. So some specific reaction rates can vary significantly with temperature, and some vary just a little bit with temperature. Okay, we'll look through some of these. I guess while we're here too, let me just kind of share, there's some important relationships that we need to know with respect to treating the mole balance. For example, we can't really measure the number of moles, but we can measure things like concentration. So we know that Ca equals Na over V. So we can express Na as Ca times V. And again, we can just plug this into here, and then we have, our term in terms of measurables. Similar for FAO, we don't measure molar flow rates, but we can measure volumetric flow rates. So FAO is going to equal the volumetric flow rate. We can express that as FV. Sometimes that's expressed in other terms in FV. So that's FV's volumetric flow rate, which is like volume per time multiplied by concentration, which is moles per liter. And now here we can plug this into here, and we have this now in terms of measurables, and we can do the same thing for the various terms. So again, plug in the RA, plug in these relationships for these terms, and then we have an expression for the rate of change of the concentration as a function of time, which gives us a model equation that's useful to solve in terms of measurables. All right, now looking at the energy balance. So another conservation equation we have is the conservation of energy. So we know that the rate of energy can change in a given system. And because we're doing chemical processes, generally we have the rate of accumulation of energy in a process will look like something like du dt equals, let me not say that. So energy, the total energy in a system is going to be U plus EK plus EP, where U is the internal energy, EK is the kinetic energy, and EP is the potential energy. So we can express the rate of accumulation of all of this within the system. So again, if we're thinking about a system right here, we have our accumulation term is occurring in our system. So we have things that enter, maybe. So we have things that enter the system, but our accumulation term is going to be what is accumulating, what is changing within this system right here, not the difference between inlet and outlet. So rate of accumulation of energy. And because potential energy and kinetic energy are generally tend to be small relative to internal energy for reaction separation processes, we're going to ignore these things and we're just going to look at the rate of internal energy. And this is going to be equal to the rate of convective heat transfer entering the system. And yeah, well, whatever the terms aside. So this is really the energy that enters through flow. So we might have here the sum of Fi Hi. So Fi is going to be the either mass or molar flow rates entering the system, and Hi is going to be the enthalpy, which is kilojoules per kilogram. Now remember that enthalpy equals U plus PV. So this is going to be the energy associated with internal energy and flow work in terms of total kilograms or kilojoules per time. So rate out, so this is going to be summed up over all of them, and this is going to be the sum of, actually this is in, sum of Fi Hi out, so same as what's entering. I don't like this term net rate of heat generation by reaction because it's not really part of the balance. This term right here is going to come into play from this the temperature, or how much the temperature changes in the reaction system is going to be related to the difference in species that exit and enthalpy that exit in the system. And so I have another lecture for you where we talk about deriving the energy balance and mole balances on reactive systems that involve changes in temperature. So I'll refer you to that video later on. And then also here, the last term that we have is the net rate of heat transfer through the system boundary. So this could be things like Q. So if we're heating using steam or cooling using cooling water, and this could also be things like work. So if we have a shaft in the system and we're turning it, if you mix something fast enough, it generates a little bit of heat. So this is our general balance. There's, some people like to talk about these types of terms here, but again, it's important to just be careful in how you're doing your derivation. So again, if we treat this properly, we can just look at flow, molar flow in, some of the molar flow in times the enthalpy in minus some of the molar flow out. And from these two terms, the heat of reaction and how it relates to the change in temperature of the process by the energy released from the reaction is going to come from those terms. All right, so there's various other types of models, and these models can be things like the ideal gas law. So PV equals, right, this is molar volume, PV equals RT, or you could have other types of gas law relationships that we use. We could have things like Raoult's law for vapor liquid equilibrium, so like YAP equals XA, PA star T. For example, Newton's law of cooling, heat transfer relationships. One of the things that we have is, especially if we have a heat jacket, is we know that Q from a heat jacket is going to be the overall heat transfer coefficient times A times T steam minus T. And we could have other relationships there as well. And we talked about some kinetic expressions where we might need the Arrhenius rate law. So this is a way to express the rate constant as a function of temperature. And we also have specific reaction rates. So for example, for a first order reaction, we could have Ra equals Kca squared. For a second order reaction, etc. Okay, so introduces a few things. So now let's look at some of the specific models for different aspects of a process. And so one specific system that is important is the dynamics of a control valve. So in many cases, chemical processes are controlled using control valves. And so the dynamics of the control valve are going to be important for the process. So in some cases, the dynamics of the valve can be fast, but in general, the valve is going to respond through a series of steps. So in order for us to increase the flow rate through a valve, if it's a, valves could be pneumatic valves, or they could be electrically activated valves. And so the dynamics of those are going to be a little bit different. But for air to open or pneumatic valves that are very common in the chemical process industry, there is going to be an increase in flow to the pneumatic system, and the increase in flow to the valve is going to cause the diaphragm to flex, and then it's going to push against the spring. So we have an increase in airflow rate, and then we have air pressure pushing against the spring to move the valve stem. So the valve stem is going to move. And in this case, what are we showing here? To increase the flow through air to open, we'll have to increase the air pressure. So that's going to push, and it's going to move the valve stem. So the valve's going to open, and it's going to reduce the constriction to the flow, and then the flow rate is going to respond to the change in the valve position. And all of this generally takes a few seconds. So control valves can generally be modeled as first order processes, and the equation for a first order process is shown here. So for a first order process, the rate of change of the flow given in this first term is equal to, this is going to be 1 over the time constant. So it's going to be proportional to the difference in the specified flow rate and the actual flow rate. So this specified flow rate could be user specified, or it could be controller specified. So if we can consider a couple of cases, we'll look at one on the next slide. So if we look at the flow versus flow specified, so if flow specified is just here as a function of time, we would expect the flow to stay on that line. But if the controller or the user causes either a change in the F specified to look like that, or a change in the F specified to look like that, then the process is going to respond. And the response isn't instantly. So the rate of change is proportional to the difference. So initially, when there is a big difference in response, the change is a lot. And later on, as it gets closer to the set point, the change is a little. So the process response will look something like that. And the first order response generally tends to show that type of behavior. Now, for a valve, the important thing also to note is that the overall process gain has to be unity, or has to be 1. What that means is when a change in the specified flow rate of 1 equates to a change in the flow rate of 1. Otherwise, the valve is not configured properly. Okay, so let's take a quick, let's divert for a second to just talk about something that's important to think about for control processes, or just processes in general. So we're going to talk about 2 different types of processes. One is called open loop process, and one of them is called a closed loop process. So an open loop process generally means a user specifies a value and specifies an actuator position. The actuator affects the process affects the sensor, and then we can read some sort of outlet to the overall process. So for example, for an open loop process, we typically have an actuator, we have a process, and then we have a sensor. And again, for a given chemical process, we might have multiple loops on a given process, multiple inputs that we can change. So in here, this is our main input. We set the actuator affects the process affects the sensor, and we have our overall output here. And for example, an input could be either F specified by our user, or it can be C, controller output. So if the actuator is a control valve, the output to the actuator is going to be a flow rate, right? And this flow rate is going to be the manipulated variable for the process. It's what's affecting the process. And whatever we care about, or we're trying to control for, or trying to measure for the process, is our control variable. So for example, if we're doing let's just say heat exchanger, the process outlet would be T, temperature. And then the sensor is measuring the temperature, and the sensor output would be TS, which is the sense value of the temperature. So a change in the F specified, there is a time delay between the actual flow rate fully responding, and then there is a dynamic component to the input to the process affecting the temperature. So increase the flow rate. It's going to take a while for that temperature to change. And then as this temperature changes, there is a response on the sensor depending on how the sensor is working. So in general, the terms that we use on here are C is going to be the term that affects the actuator. U is going to be the manipulated variable, the input to the process. Y is our process variable, YS. So we can also have a filter. So if in the case of a noisy sensor, this sensor value can go through a filter and give us YF, the filter value of the process. Okay, so in general, though, we don't necessarily treat filters in open loop processes. So here's open loop. For a closed loop process would involve a controller. Okay, and what the controller is going to do is the controller is going to take the measurement of the sensor, and it's going to take a specified value, and the controller is going to set the specified input to the process. So instead of the user inputting the setting or the valve position on a valve, the user inputs a specified value on the control variable for the process. Again, we'll initially in this class, when we talk about our models, we're going to derive models for, we're looking at what is the model for an actuator. And we just said a model for an actuator is, one example of a model for an actuator is first order. We're going to look at various models for processes, a couple of different models for sensors. And then as we move forward in this course, we'll look at what is the model for the controller. And maybe you've heard of PID before, the proportional integral derivative type controller is the model that we're going to look at for process control. All right, so let's go through. There are really two types of models that we can do for an actuator. So if an actuator responds first, generally if it's a control valve can respond first order. And as we saw, the model for a first order actuator is df dt equals 1 over the time constant, and then F specified minus F. So what this means is if F specified is greater than F, this overall term is positive and the flow rate should increase. That's what we would expect. So we can also have what's called a fast actuator. And if an actuator responds fast, what that means is that the flow rate, and again, flow rate is a function of time, equals F specified. So if you change, so for a fast actuator, a change in F specified would result in an instantaneous change in the flow rate. And these are useful models when the dynamics of the actuator are significantly faster than the dynamics of the process, such that the actuator dynamics don't affect the overall control scheme. So those are the two models for actuators. So actuators shown here. So now let's look at our sensor model. So for sensors, we can also have a first order sensor. And again, this model is going to look very similar. So the output, we're modeling the output. So the output of the sensor is DTS, dt. So the rate of change of the sensor, if it's first order, it's going to be 1 over the time constant of the sensor. And then let's see, what do we have here? So we have the time constant of the sensor is going to be T minus TS. And just to double check, if the temperature of the system is greater than the sensor temperature, we would expect the sensor temperature to raise. So this term is plus, would result in this term being plus. So this is this is written correctly. Now remember, all of these terms are a function of time. TS is a function of time. T is a function of time. Let me just rewrite this to make it minus TS. Oops. I'm getting ahead of myself and putting us in the Laplace domain. We don't want to go there yet. TS is a function of time. We can also have a fast sensor. And as you might expect, TS as a function of time equals T. Changes in the process respond instantly. And then finally, we have what's called a lag or dead time. So oftentimes, sensors are based on sampling systems where you have to take something out of the process, put it in another instrument, or it kind of go through some sort of cycling process. That can be done automatically, but it goes through some sort of sampler and gives you a value. So for, let's see. Yeah, for our sampling sensors, we have TS as a function of time equals T of so equals the temperature at some delay, some time ago. So the temperature of a sensor right now is going to give us, it's going to be based on a sampling reading that was made some time ago. And so this is the dead time, or the time that it takes to do the actual sensing. We should also mention here that we'll look at how to treat this in the Laplace domain, and we'll look at how to treat all of these in the Laplace domain, because ultimately what we want to know is how do inputs affect outputs. And so in each one of these equations, we have the output on the left, which would be either the sensor or the flow, and then the input is on the right. So the input to the sensor is the temperature, the input to the actuator is the F specified, the output is the flow. So what we're looking at is the dynamics of how inputs affect outputs. So these, good news is these are all the models that you need to know for actuators and sensors. So just be familiar, or just pay attention to what does the problem say, or what is the components of the system. Okay, so here's the dynamic response for a valve or a first order process. So this is shown here, and this was really going to be any first order process. And so remember, F specified is the input, F is the output. So in this case, we have dF dt equals 1 over tau v times, was it F specified minus F. Okay, so what's going on in this process right here is that here's our F specified. At time equals 1, the user had a change in F specified from the initial value. So this right here would be F specified 0 to F specified. So there's a change. And so because this is a first order response, immediately when the difference between F specified and F is large, the rate of change is large, because right when this term is large, this is going to be large. When this is small, the rate of change is going to be small. So as we approach the value, this change over here is going to be small. And so first order process is going to look just like this, kind of a steep starting, and it's going to asymptotically approach the new value. So the dynamic and it's always going to look like this. So this is F plotted as a function of time, and this right here is F specified, our input, as a function of time, which is just a step function. So this plot right here, what it shows us, to be specific, is the dynamic response of a first order process to a step change in the input. All right, so dynamic models for sensors. So again, like we said, let me see. Okay. So the dynamic model for sensors, they can be first order. We just showed you what they are. The dynamics can be fast. So it can be first order. It can be fast, and the gain on the sensor. So the first order sensor can have a time constant associated with it, but the gain on a sensor always needs to be 1. And the reason why it needs to be 1 is for at least a well-calibrated sensor, if your temperature changes by 5 degrees, your sensor should also change by 5 degrees. So the rate of change of this output is the same as the amount of change of the output is the same as the amount of change of the input. Okay, we mentioned that some models, some types of models can be composition or sampling type models. In a sampling type model, we said that the CS equals the composition, the value of the sensor equals the composition some time ago. So let's just think about how this would work. If shown right here is the actual composition in our, let's just say the composition in our reactor or in one of our outlet streams from a separator. If we take a sample, oh no, I don't want to erase that. So here is our composition. Okay, imagine we take a sample at this point right here, and it takes us, theta A is our sample time. Okay, if we take the sample at this point right here, we will have the new value. So the value of this right here is going to be, at this point in time, we took the sample right here, and the value was equal to this. And it just so happened to be, we took the sample right at the time that the change started to be made. It could be slightly before, it could be slightly after. We're just taking the sample every certain amount of time. And then at this time, so we reported this value. Then at this time, we took the sample here, and then we report the value after theta time. So then we report this value right here. At this time, we take a sample again, and the value is reported here. Take a sample, value reported, take a sample, value reported, etc. So if we want to look at like the analog or the actual signal, what it's going to be expressed by the composition is during this time when there was no change, and then the value reported there was no change at this time, so that the sensor reading would stay here until we had this new value reported, and then it would be this, and then it would be this. So our sensor value, our sensor curve is going to look something like this. And we could, if we wanted to if we kind of extrapolate through these points, what we see is that it's the same function, but it's just the function shifted by a certain amount of time, which is the dead time or the sample time of the sensor. All right, so we've covered actuators and sensors. So now let's go through a couple models for processes. So the first model that we'll look at is the level on a tank. So draw the system, it's shown here. So we have flow in, we have flow out, we have a valve, which means we're probably going to control the flow out, but we could control the flow in, doesn't matter. So first of all, let's think about what are some of the things that we can control in a process. So we can control things that we can measure. We can't control things like energy. We can't control things like moles. We could control concentrations, but not moles. So we can measure temperature, so we can control it. We can measure pressure. We can control pressure, flow, level, composition. I don't know. Are there some other things you can think about what you might be able to control? Typically, then how do we control these? We can control things using flow valves, using heating, for example, steam. So for heaters, we could use steam, so we can control the pressure or temperature of the steam, which is going to affect the heat transfer rate. We could have an electric heater what we just changed the power to. We can control cooling water flow rates, maybe temperatures. We can control mixing rates, things like that. So those are generally the handles that we have, but oftentimes we're going to be changing a valve that changes a flow rate or temperature or pressure. You may have a variable speed pump where you control the power to the pump, or which is just directly controlling the flow. But in any case, the balances here are going to be kind of similar. So let's look at this. So if we want to control the level in the tank by controlling the flow out, we need to have a relationship between the level in the tank and the flow out. And to do that, we have to start with the conservation equation. So let's conserve mass. So our system is going to be the tank. So we're looking at this right here. So the rate of change of the mass inside this tank is going to equal the sum of mi in minus the sum of mi out. Oops. And that's it. And I can write it as total flow rates. I can write it as different species flow rates. I can add them all up together. I could do, I could do mass balances on individual species. But for this right here, because I want to control the level, I want to consider the entire mass of the system. Okay, so I could have other streams in F2, etc. And, we could treat those on there. I'm not going to do that right now, but you could do it and it doesn't necessarily change the balance. But now I need to put this in terms of measurables. So I know that the mass equals rho times V, and I know that V equals AC times L. So my mass for the system is going to be rho AC times L. And so my MI, my M in equals F in. I'm assuming that this is a mass flow rate. And so what I need is, because I'm controlling the flow, the volumetric flow and not the mass flow, I need to convert this in terms to volumetric flow rates. So in terms of volumetric flow rate, so this right here is mass flow. To convert it to volumetric flow rate, I need the density times the volumetric flow rate in. And then the same thing for the mass and the volumetric flow rate out. So when I put these things together, plug this term up into here, and I know that I'm going to assume density, cross-sectional area, those stay constant. So I have rho AC dl dt equals rho FV in. And again, if I want to be specific, I should say rho in, because maybe the density of the species entering is different than that of the system, minus rho out times FV out. But again, I know that rho out is equal to rho because the stuff that's coming out is the same as the stuff that's in the system. So I can just call that rho, FV out. And again, if I assume that the density of what's in the system is fairly constant, so density is constant, then I have AC dl dt equals FV in minus FV out. And this would be my model for this overall process. So this is my output variable, and then my input here is the flow rate into the process. And again, remember from the actuator equation, this FV out is going to be the output of the actuator equation, where we have a specified value that would be the input. So for the actuator on this part right here, we would have dFV out dt equals 1 over tau v f specified minus FV out. I'm running out of space a little bit, but you get the point there. We could do some other things too, and let's just do like, I want you to maybe think about something on the side. What if, so case 2, outlet flow by gravity, control inlet flow, FV in. Okay, so now our model is going to be similar. And so what I'm going to do is I'm just going to start from the same equation that I have. I would really derive it starting from 0. So we have FV in. Okay, now this is our input. And this right here is now our output. And so if the flow out is driven by gravity, I know that the flow out, so flow out driven by, is going to be equal to some sort of constant times CV times delta P over rho. Let me write that. Let me write this a little bit better. So the flow out of a tank by gravity. So the flow out is going to be, or just the flow out of a system is going to be equal to some sort of, unit conversion constant times CV times square root of delta P over rho. And then we also know, and then also that should just say, typically this is about 0.61 for a tank. And then I also know that delta P equals rho GH, the height of the fluid, which here is the L. So out of these terms, all of these terms right here are effectively constants except for L. So I can just group those constants together into a new constant. I'll call that, little k1. So this right here, FV out is going to be little k1 times the square root of L. So now we have our output variable. Our level is going to be now part of our equation, and we have to, treat that, because as the level of the tank changes, it's going to affect how much flow is going out. And so that's important to consider. So a couple different cases we can think about for treating the level in the tank. Okay, the dynamic models. We talked about these enough already. You can write the dynamic models there. I guess I should say that on the last one, on this one, the level sensor is assumed to respond much faster than the process of the actuator measures the level accurately and instantaneously. In that case, we know the level sensor equals the level as a function of t, and oftentimes level sensors respond that way. Okay, there we go. That's what that would look like. Let's look at another process, a thermal mixer. And so in a thermal mixer, we have two streams that are going to mix together. It's well mixed. So we have F1T1, F2T2, and then FT coming out. And so our assumptions here on the thermal mixer are well mixed, constant volume. Maybe we'll say some more there, but what we might do in this process is we probably control the flow rate of one of these streams. And I'm being sloppy on my drawing, so let me do that better. So we probably control the flow rate of one of these streams, and we care about the temperature of the system process coming out. And so I'll say that well mixed constant volume, probably what this means is the outlet stream, the outlet flow is controlling the volume. Right, so we're varying this outlet stream right here, and it's keeping the volume constant. This flow right here, we use that to keep the volume constant, and we're going to look at varying the flow rate of F1. So our manipulated variable is going to be F1, which is our input, and our control variable is T, which is our output. So we want an equation that relates how the changes in the input F1 affect the changes in the output T. Okay, so what do we need? We need here an energy balance, or we need to, well, I guess we could first do a mass balance. And I guess what I want to say is, one thing that we know because we have this constant volume, we can say that F equals F1 plus F2. And this is also the same as our mass balance. Again, assuming constant density. And it'll be an okay assumption unless the temperatures vary like wildly. But then again, we're keeping a constant volume. So volumetric flow rate out needs to be volumetric flow rate in, but mass flow rates might vary a little bit. All right, let's do our energy balance. We have rate of change of energy with respect to time equals the energy in due to flow. So the energy in due to flow is going to be F1H1. So again, this might be mass flow rate, mass per time times energy per mass plus F2 times H2. minus F times H. So in this case right here, we don't have Q. Well, let's add Q. Let's put a heater on here. Do we want to put a heater on here? We could put a heater on here. We could maybe say we could have Q. Maybe it's a steam jacket. Maybe something else. And we won't really treat Q, but if we do have a Q on here, plus Q, so the heat added. We can also have plus shaft work, but here we're going to assume that the shaft work is negligible relative to the changes in internal energy. So yeah, if we had Q, we can use it. We'll just keep it on there for now, and we can treat it with or without. We need a relationship for U. So I know that U is the total internal energy. That's going to be equal to the mass times the intrinsic internal energy. We also know that du equals CV dt. So if I use all of this information together, this first term is going to be m times CV dt. And this is assuming that the mass stays constant and the heat capacity doesn't change very much with temperature. And that's okay because we don't expect the temperature to change very much. All right, so let's group some of these other terms over there together. So this term F right here is F1 plus F2. So if I put these two things together, I'm going to have F1 times H1 minus H. And then I also have plus F2 times H2 minus H. And this right here is just a delta H, and delta H equals Cp delta T. So this is going to give me F1 Cp. And then H1 is associated with T1. H is associated with T plus F2 times T2. Oops, maybe need Cp here as well. And then I have T2 minus T. And then also, maybe we still have a Q. Maybe it's Q from steam. Like if it's Q from steam, we'll look at that. Hold on. Okay. So other things that we might, so here we're kind of close now, and maybe I might stop here for a second because here's our mcv dt equals F1 Cp T1 minus T plus F2 Cp T2 minus T plus, if let's just say Q is based on a steam jacket, Q would be equal to UH times the heat transfer coefficient times the area times the T steam minus T. Let's just say if it's equal to that. And again, all of these things are constant. And so in here, this equation right here, we have our output variable T and all these terms right here, and then our input variable F1. So we know how temperature varies as we change F1. There's also other assumptions we can do. Because it's a liquid, Cp is approximately equal to Cv. And so we can make that assumption, or we can then cancel out those terms. And if we do that, let me bring this over here. If we cancel out those terms, we just have to be careful. Cancel, 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 divided by Cp in this term, in the heat transfer term. And we could group things in a different way. But in general, that gives us the equation that relates our output variable to our input. All right, let's think about composition mixers. And again, I'm not going to spend a lot of time on this one, but composition, we could have the same sort of process where we have F1, C1, and here we're just treating a single species in a solvent, like perhaps salt in water. And these are two different variables, F and C coming out. All right, and so in this system right here, we would just write the mass flow rate on the individual species. So the mass flow rate of species 1, let's see, the rate of change of species 1 in the tank equals that which is flowing in. So we're going to have how much is flowing in. So we have F1. This is going to be, let's call this FV1 because this is going to be volume per time multiplied by concentration 1. And this is going to be mass per volume. So over here we have mass per time as all the units in this equation. So volume, so this gives us mass per time. So plus FV2 times C2 minus FV times C. Now remember here that because of the assumptions before, we know that FV equals FV1 plus FV2 to keep the level constant. And we can do some simplification, substitute measurables for things that aren't measurable, and get to a similar equation that we had previously. So I'll let you finish up that one. And the last example that I wanted to do here was just briefly look at a reactor. And I have another system where we look at reactors that involve chemical processes. So in this case right here, the model for a CSTR reactor. So it's a continuous stir tank reactor that has a series reaction. So in this case, we want to control the composition of the product. And, we could be measuring species A, species B, or species C. I think what we care about right here, for this example, let's say we care about the concentration of species B. We're controlling for that. So because that's what we're controlling for, this is our outlet variable, and the variable that we can change, it looks like the flow in. So our input is FV in into the system. So let's just go ahead and start with our balance on our concentration of the product. So we'll do a mole balance. We'll balance moles of species B. So mole balance is the rate of change of the number of moles of species B with respect to time equals FB0. That's FB entering minus FB coming out plus the rate of change of the reaction rate of species B times volume. And so there's no B entering the system. Again, I need to put this now in terms of measurables. The number of moles in B equals the concentration of B times volume. FB equals the flow rate. And again, we're assuming constant volume, so constant flow rate in, constant flow rate out, volumetric flow rates, times the concentration of B. And then we have the reaction rate for species B. So let me substitute these terms in, and we have V times dCB dt equals negative FV times CB. So again, we have this right here is our input, CB is our output, and the rest we have are constants. Now RB, so the reaction rate of species B. So species B is both being formed and it's being consumed. So RBV is going to be plus R1. So we have, it's going to be plus K1CA squared V minus R2, and it's being consumed by minus K2CB. Okay, so if we look at our model equation now, we have our input, we have our output term CB, our inputs, our variables, but now we have this other term CA that can change as a function of time too. So other than our input and our output, we now need a model equation for our species A. So let's just write the mole balance on species A, similar to before. So dNA dt equals FAO minus FA plus RAV. And similar to what we had before is we have V dCA dt equals FAO is going to be FV minus FVCA And then the reaction rate for species B is going to be minus R1, so minus K1 Ca squared. So now here we have, just in terms of our input, and here our Ca is our output, and the rest is constant. So that's how we do our mole balances for reactors. Okay, so that's all we're going to do for our model derivation, but there's a variety of models that are discussed in Riggs textbook chapter 3, and really those that we do, or those examples in the book, are the ones that we've talked about here, or the ones that are on the homework, are really the ones that that you'll be responsible for this class, in terms of, testing and examples that we're doing moving forward when we derive other types of functions from the model. So it's important to get our models correct so that we can derive the next set of functions that are more convenient ways to relate inputs to outputs. Okay, so generally the dynamics of the overall control system is going to be based on all of the individual components. So you can kind of pause and read through this if you'd like. So the way that information flows through a process is shown here. So we talked about this already for an open loop. So we'll set the value to the actuator. The actuator will respond and affect the process. The process will affect the value we care about, and that will be measured by the sensor. And all of these has their individual dynamics associated with them. We kind of talked about which term, the independent variables, the dependent variables. Those are the terms that are the differential terms in the equations, and then parameters are just other terms that are needed. Degree of freedom analysis, you've seen this hopefully various times before, and really all that matters here is that we need the same number of equations as we have unknown variables. So in order to solve the system, we need the same number of equations as we have for unknowns. If we have fewer equations than unknowns, we won't be able to solve the system. If we have more equations than unknowns, it's possible to have multiple solutions, and multiple solutions will not be consistent with each other. So no real solution exists. We can also do things like model sensor noise. We will look at this later on in the control station workshop, and how that affects the process. And one of the ways that we solve the differential equation is using numeric integration. We're not really going to study this too much in this class, but numeric integration is a tool that we can use to solve for the systems, to see how the parameters are changing with respect to time once we're able to derive the set of model equations. So in general, you should be able to derive the simple process models from the basic conservation equations. And the idea is converting from things that we know into things that are measurable. Later, we'll look at kind of deriving processes from actual model responses, something that'll be a little bit more practical. And as we go forward, the next step will be to use Laplace to convert from time domain to Laplace domain, and use those to derive what are called transfer functions. And transfer functions give us algebraic equations that relate inputs to outputs for a given process. So that's all we're going to do today, and we will talk to you next time.